So just by way of a quick review, in case you didn't watch the previous lecture, what we're looking to do is develop a solution to what's called the traveling salesman problem. Right? So in technical terms, our goal is to find what's called a Hamiltonian circuit around a weighted graph like the one I've got here on the left that has the additional condition that it has the lowest possible cost. Right? And kind of in the context of a traveling salesman, you're a traveling salesman, the vertices are the cities in your territory, the numbers are the travel costs, and you want to find a route where you visit every city exactly once, you end up in the same city that you started from, which presumably where you live, and the cost is at a minimum. Remember, we discussed the problem with this is that there are no known perfect solutions to this that also can be counted on to run in a reasonable amount of time, even for graphs that are starting to get really large. So absent those perfect solutions, what we kind of fall back on is trying to find solutions that may not be 100% right all the time, but that at least give us good results most of the time. Okay, sometimes that's the best you can do. So that's what we're going to talk about here. Specifically, we're going to talk about a method called the nearest neighbor algorithm. And I've got the procedure outlined here below, and obviously we'll go through some examples. But the way this works is you start with a graph that has just the vertices of the original graph. We're going to strip out all the edges. Then we're going to select a starting vertex. You get to pick whichever one you like. Then we're going to locate the nearest neighbor to that vertex, the one that's closest to it, and we're going to add that to our graph. And we're going to keep repeating this process, right, until one of two things happens. Either adding the least cost graph would create a circuit, which we want to avoid. We don't want the graph to close up prematurely, in which case we just skip that and move on to the second best edge. Or we've added all the edges, in which case we close up our graph, right? We add the edge connecting the last vertex we ended up on to our starting vertex, and we're done. There's our result. Now, if you think about this for a minute, that step 5 is potentially problematic. There may not be an edge connecting that penultimate vertex back to the one from which we started. Now, in a graph like the one here I've got on the left, this is a complete graph. You remember that's a graph where every vertex is connected to every other vertex. In a complete graph, yeah, okay, there always will be a way to close it up, as it were. But there may not always be, right? You may be dealing with a graph that isn't complete, so that is a potential concern with this method. Okay, so with that said, let's look at an example. This is the same graph from the previous slide on the left. And on the right, I've got just the vertices. I stripped away all of the edges. So what I'm going to do, not for any particular reason, just starting at the top, let's start our circuit with vertex A. And if you look at all of the edges going out of vertex A, their costs are 13, 8, 5, 15, and 11. I'm going to pick the lowest one. So I'm going to take my graph, and I'm going to add that 5 weight edge connecting vertex A and D, and I'm going to remove it from the original graph so I'm not tempted to accidentally add it again. All right, now looking at vertex D, there's 4 edges coming out of that one. I've got a 9, a 7, 2 9s, 3 9s, and an 8. Okay, the 8 wins, so I'm going to add the edge connecting D and C and remove that from the original graph. All right, hopefully you've got the idea now, right? We're going to just keep doing this over and over. Coming out of vertex C, we have 7, 4, 9, and 14. That 4 edge going to vertex F is going to be the least cost. So I'm going to take that one out of the original. And here's where things get a little interesting. Coming out of that F, we have a 13, a 9, and a 13. Well, I'd like to add the 9, but I can't, because the 9 connects vertex F to vertex D. And if I add that one, then I've created a circuit between vertices F, D, and C, and that's not allowed. So I'm just going to remove that edge, and I don't have anything to add yet. Right, so now I'm down to 2 13s and a 15. I forgot to mention that 15 earlier, but that's okay. It definitely wouldn't have been the winner. So now I have to pick one of the 2 13s. Well, the 13 connecting A and F, if I added that, it would also create a circuit. So that one's out of the running. And that leaves me with the 13 from F to E. And again, I'll remove that from the original graph. And now we're starting to run out of options. Coming out of E, I've got a 7 and 8 and a 9. I've got a 6, 7, 8, and 9. So I can add the 6. That's the lowest one. And we'll remove it. And I want you to take a step back and look at what's happened. I have connected all 6 of the vertices. Right, so all that's left here is to close up my circuit. So I'll go back to A. That was the only one that didn't create a circuit. And that gives me my path. Right? Or excuse me, that gives me my technical term, Hamiltonian circuit around this graph. Right? It's going to go A, D, C, F, E, B, and then of course we'll go back to A. And the total cost, if you add up all of the edges that I removed here, the total cost of this one is going to be 57. Okay, so hold on to that. Right, hold on to that. So what I'd like to do now is do this again, but this time start from vertex F instead of vertex A. All right, so if you can pause this lecture if you like, if you want to walk through this on your own, right, then start it back up and we'll go through this together. All right, the least expensive edge coming out of F is that 4 going to C. So we'll add that one first and remove it from the original graph. Now, coming out of C, our options are 14, 15, 7, and 8. All right, so the least cost edge is going to be the 7. You see, things have gotten interesting already. That edge from E to C was not in the circuit that we ended up with in the previous question. So already we've gotten a different result. We'll talk more about that in a minute. All right, so coming out of here, our next least expensive edge, I think that's going to be the one from E to B. That'll take out a 6. Coming out of B, my options are 11, 15, 9, and 14. So I'm going to add the 9. Going down to D and remove it. Coming out of D, I've got 2 9s, a 5, and an 8. The 5 would be the least cost, so I'm going to go up to A, and then I'll close the graph, right? Close my circuit, connecting back to F. And as you can see, yeah, we did get a different result here. Now we have F, C, E, B, D, A, F, and the total cost was only 44. Total cost was lower. Okay, so what happens? Well, what happens is what I warned you was going to happen with this particular method. It generally speaking will get good results, but we can't be guaranteed that it is always going to find the absolute best result. So this is a class in graph theory. We're talking about it at the moment, not a class in algorithms. But I do want to talk for just a minute, since a lot of the people watching this will be computer science students, about the algorithmic aspects of this. This nearest neighbor method is an example of what, in algorithm design, is called a greedy algorithm. And a greedy algorithm has a couple of characteristics. First, it's based on making decisions, right? You build solutions by making a sequence of choices. And you saw that in what we did, right? At first, I chose the starting vertex, and then I chose the best vertex from there, and then I chose the best vertex from there, and so on. So it was a sequence of choices that I was making. And each decision is based strictly on local conditions. So when I was picking the next vertex, All I looked at was the next vertex relative to the vertex I was currently on. A greedy algorithm has no capacity to look ahead and say, well, you know, I know this is my best choice now, but if I make that choice, it's going to force me into situations down the road where I have to make some really bad choices. That's the sense in which this is greedy. It's very much in the moment, right? It has no way of looking beyond that. So some of the downfalls of greedy algorithms, and we saw this in our example, the order in which the choices are made can significantly impact the outcome. In this case, my very first choice, what my starting point was, made a pretty decent difference in my final outcomes. Another area where this can come up when we almost had this happen is, what about if you have a tie? What if you have two vertices, both of which have the lowest cost? Well, with greedy algorithms, what you'll usually do is choose at random, right? Where, again, if you're kind of a human looking at this, you want to say, okay, well, what's my next choice? If I choose option A, what's my lowest cost choice from there? And if I choose option B, what's my lowest cost choice from there? And you can kind of use that next step to inform your decisions. Well, greedy algorithms can't do that. They're all about what's happening right here where we are at the moment. And finally, as we saw, these algorithms are good. They're often really pretty efficient, but they may not always get the absolute best result. So this is one approach, right? In the next lecture, we're going to look at another one of these greedy algorithms for finding a Hamiltonian circuit through a weighted graph, or solving the traveling salesman problem. One that's called the best edge algorithm. Right, so there's a link to that down here at the bottom. And if you like this video, please don't forget to click the like button down there as well.